All right, workout 5 for lesson 29, or the first workout problem 5 on the handout. So we're looking at two different cylinders. We've got a solid cylinder here, and we have a hollow cylinder, both rolling down this ramp, starting from rest. So if we take a look at this, we're going to start with gravitational potential energy at the beginning because we're starting from rest here, and then at the end we want to know how much kinetic energy they have. So they're going to have some type of rotational and some type of translational kinetic energy. We're looking for the velocity though. So if we break this all out again, we have mgh has to be equal to 1/2 I omega squared plus 1/2 mv squared. So we've got, we'll have cylinder 1, and for this one, we've got mass of m1. So we have m1 times g times h has to be equal to 1/2, and then we have to figure out I. So we want I for a solid cylinder. So if we go to our equation sheet, we can look up disk or solid cylinder here. So we've got 1/2 mr squared that we're going to put in for I. So I is 1/2 m1, and then the radius is r squared. So there's our I, and then we have omega squared plus 1/2 m1v squared. Now, as we look at this a little bit more in depth, what we should find is that omega, right, is v over r, and we can look at that on our equation sheet. So here's omega and v, and they're related by r, so omega is going to be v over r. So if we come back here, we can swap this out for v over r, and that whole thing is going to be squared. So what that gives us, though, is that r squared is going to cancel with those r squares, and we can go ahead and rewrite this out. Oh, actually, one more thing. Those m1s are all going to cancel there. So we have gh is equal to 1/2 times 1/2 times v squared plus 1/2 times v squared. And if we simplify this out, what we wind up with is v is going to be equal to square root of 4gh over 3. Take a look at cylinder 2 here. So in the same vein, what we're going to wind up with is m2gh equals 1/2 I. Now I for a hollow cylinder for m2. So if we come back to our equation sheet, we take a look, we have hollow cylinder is just mr squared. So this would be m2r squared, and then omega squared again is just v squared over r squared plus 1/2 m2v squared. So if we go through and we cancel everything, our masses are all going to cancel, those r squareds are going to cancel, and we just get left with gh equals 1/2 v squared plus 1/2 v squared. When we solve that out, we wind up with a velocity that equals the square root of gh. So We have now found expressions for the final velocities for both of those cylinders at the bottom of the ramp. Problem 6 on the handout, or workout 2. Once again, we're using our conservation of energy, so we know the gravitational energy at the top of the ramp has to be equal to the kinetic energy at the bottom of the ramp. So in this case, we have mgh has to equal our kinetic energy. So if we plug in our specific numbers, we have 2 kilograms times 9.8 meters per second squared times the height, which is 7.5 meters. And if we figure all of that out, what we should come up with is that we have 147 joules of kinetic energy at the bottom. What is the translational kinetic energy at the bottom of the ramp? So for this one in particular, we're looking at translational kinetic energy. So if we take a look at this one, we know our total kinetic energy, K, is 147 joules from up here. And now we know that that has to be equal to both types of kinetic energy. So 1/2 I omega squared for our rotational kinetic plus 1/2 mv squared for our translational kinetic energy. So we're trying to find how much translational kinetic energy it has. Now we know it's a solid cylinder, so I, if we rewrite this again, our I, we can go back to our equation, and disk or solid cylinder, right, is 1/2 mr squared. We have 1/2 mr squared for I, and then omega. Does it tell us? No, but we do have the, oops, we can do V over R squared plus 1/2 mv squared. Let's just rewrite this down here. Equals 1/2 mv squared, but we set our velocity, right? What we're going to be using is square root of 4gh over 3 squared. So in our context, 1/2 m, which is 2 kilograms, times the square root squared, so that's going to go away. We just get 4g, which is 9.8 meters per second squared, times the height, which we said was 7.5 meters, all over 3. And if we solve all that out, we should wind up with 98 joules. All right, the rotational kinetic energy at the bottom of that ramp. This one, we said Kr is equal to 1/2 I omega squared. And from earlier, we looked up I, which is 1/2 mr squared. And then omega, which is V over R, both squared here. Well, those R's are going to cancel with each other, and we wind up with something that's 1/4 mv squared. So if we plug our numbers in for this, we get 1/4 2 kilograms, and our velocity there, if we solved all that out earlier, 9.9 meters per second squared, and that's the same velocity here. It's just going to get plugged in. We plug those numbers in, and then that gets squared. So when it's all said and done, we get something that's 49 joules. Let's start off this problem here with our conservation of energy equation. So we have U, gravity, plus U, spring, plus kinetic rotation, plus kinetic translation has to equal U gravity plus U spring plus kinetic rotation plus kinetic translational. So now, point 1 is going to be when the spring is fully compressed. And nowhere in here does it say anything about gravity. So we can, let's do this one. Gravity goes away. And before we start moving is when the spring is compressed, so that we have no kinetic energy. Now, after we release it, we still have no gravity. We're at the same height. And the spring is no longer compressed, so we have no spring, but we are going to have rotational and kinetic energy. So, just simplifying this a little bit, we have the spring potential is equal to the kinetic plus the kinetic. Now, we're going to have to break this down a little bit further, and if we remember, our potential for the spring is 1/2 kx squared. Our rotational inertia is 1/2 I omega squared, and then our translational kinetic is 1/2 mv squared. Now, we'll simplify this just a little bit further. 1/2 I, so this is a solid ball here that we have to look up. So if we go to our equation sheet, we've got a solid sphere, or 2/5 mr squared for I. So in this case, we have 2/5 mr squared, and then omega squared. But once again, omega is just v squared over r squared, and then 1/2 mv squared. So r squareds are going to cancel, so it doesn't really matter how big the ball is. If we just manipulate this algebraically first, what we should wind up with is velocity equals 1/2 kx squared over 1/2 m plus 1/5 m, all under the square root. And if we were to plug all these numbers in, what we should wind up with is 16.8 meters per second. Translational first, 1/2 mv squared. So in this case, 1/2 m, which is 0.05 kilograms, and then our v, which we just found at 16.8 meters per second. That winds up being about 7 joules. And our rotational is 1/2 I, which we found earlier, which is just 2/5 mr squared times v squared over r squared. Those r's go away, and so when we write this out, those 2's will actually also cancel on this. 1/5 mv squared, which is 1/5 0.05 kilograms times 16.8 meters per second, and all that winds up to be 2.84 joules. 7 joules and 2.84.